Hello everyone, welcome to the video. Today we are going to solve the problem longest palindrome in a string. In this problem, we are given a string and we have to find the longest substring which is also a palindrome. For example, for this string, this is the longest palindromic substring. While this question is a simple one and there exists a non-recursive solution for it, but one must also try to solve it using the recursion, dynamic programming, memoization and bottom-up approaches. Why? Because if we get comfortable thinking through these approaches, these will serve as building blocks to solve multiple problems. There is an interesting complexity where a candidate may be asked to optimize space even more than what a simple bottom-up solution would provide. We are going to solve this problem today. We are not going to directly jump to the solution, but gradually think through and build the solution. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's start. To begin with, let us first note the key things down from the question. We are given a string S and we have to return the longest palindromic substring from this string. If this is the input string, then our output will be this substring. This is a substring of the original string. It is a palindrome and it is of the longest possible length, which is a palindrome. For example, in this string, even BB, AA or even individual characters are palindromes, but they are not the longest. So we are returning this string as our answer. So if we consider our solution as a black box, we are getting string S as input and we have to return a palindrome string as output. So what will our function signature look like? Our function signature will look something like this. Let us see what will be the simplest way of thinking about this problem. For the input string, we need to find a substring. That substring has to be the palindrome and it has to be the longest possible palindrome. So one way we can think of is, let us get all substrings, check if they are palindrome and find the longest among those. How will we get all the substrings? So there is a very common approach for that using nested loops, two nested loops. In the first loop, we fix the starting point of the substring using pointer I. In the second loop, we fix the end point for the substring using pointer j. Once we have the candidate substring, what should we do next? We should check if this is a palindrome. If this is not a palindrome, then that substring is of no use to us. But if it is, we need to check if this is the longest palindrome so far. How will we check if this is the longest palindrome so far? For that, we will need to maintain what we have seen as the longest so far. If it is a palindrome, we will check if it is longer than what we have seen so far. If it is longer, then we will update our longest what we have seen. At the end of all iterations, we will return the longest palindrome seen so far. Now this is the approach which is simplest enough. The only thing that we now need to solve is how do we check if any string, any given string is a palindrome. This is a very common problem where we are given a string S and we have to check whether this string is a palindrome. Now first of all, what is a palindrome? Consider this string. This string is a palindrome. Why? Because if I read this string from left to right or I read this string from right to left, in both cases I will see A, B, C, B, A, A, B, C, B, A. Therefore, this string is a palindrome. So we can definitely notice one thing, that if we have two pointers here, one I to the left extreme and one j to the right extreme, the characters at these two pointers will be same. If we advance these two pointers, let's say we advance I by one position to the right, we advance j by one position to the left. Now the new characters at these positions will also be same. Therefore, this is the key insight that we will use to check what if this given string is a palindrome. Now first consider the length equal to 1 strings. If these are the length equal to 1 strings, let's say A, B, are these palindromes? Yes, because we are reading it from left to right or from right to left. They are same. Therefore, these are palindromes. But if we consider for length equal to 2, whether all the length equal to 2 are palindromes? No, because this is AB from left to right and BA from right to left. But length equal to 2 are palindromes if both the characters are same. Therefore, what will be our approach if the string length is greater than 2? How will we check whether this is a palindrome? We will fix 2 pointers I and j and we will try to use this inside. So we will iterate. Now what will we have in every iteration? In every iteration we will have the character at I, we will have the character at j. So we should check if these two characters are equal. If these are not equal at any position, we have to return false. And if after all the iterations we did not return false, that means everywhere characters were equal. Therefore, we can return true that this is a palindrome. And till when we will iterate? We will iterate till I and j meet. What will be the time complexity of this? The time complexity will be big O of n, because where n is the length of the string, because we have to traverse across the length of the string. Now let us see what will be the time complexity of our approach to solve the problem longest palindrome in string. We are first selecting a candidate substring using 2 nested loops. So that will take big O of n square. Now once the substring is selected, we are checking if this is a palindrome. Right from previous slide, we can see that this checking of palindrome will take again big O of n. Therefore, total time complexity of this solution will be big O of n cubed. But this is inefficient. Why? What is the inefficiency that we are doing here? Consider this string ABCBA. Let us say we had to check if this string was a palindrome. We could find and say that yes, this string was a palindrome. Now let's say there comes another substring, which is nothing but we have added D to start and end of this string. Now we have to again check if this is a palindrome. Now, does it make sense to go through this whole string and check if this is a palindrome? It does not, right? Because we already know that this part is a palindrome and we have just added the same character to start and end. So overall, this will also be a palindrome. Now this was just length 5 here. What if this was length 50 or even higher? So much time would be wasted in computing all of this, whether this is a palindrome or not, by checking all the characters. So the solution that we discussed in the previous slide, that takes string as input and returns a boolean as output, that works well if we have to pass an individual string and check if this is a palindrome. But if for a string we have to check for it all of its substrings whether these are palindromes or not, then this solution will be inefficient. Why? Because this is not able to use the results of past substrings which we have already calculated whether these are palindromes or not. This is a common problem where we are given a string S and for that string we have to check all of its substrings, and for all of those substrings we have to give the information whether that substring is a palindrome or not. So before solving this, let's figure out its input and output types. We know that input will be simply string S. But how will we represent the output? For output, we have to represent this information that, hey, this is a substring and whether this is a palindrome or not. So what can we use? We can use something like key value pair. Now, what will be the type of value? Value is just true or false, whether it's a palindrome or not. So value can be boolean. But what will be the type of key? Key is basically representing a substring. How can we uniquely identify a substring? We can uniquely identify a substring by a pair I, j, where I is the starting position of that substring and j is the ending position of that substring. But like we could say that the value is of type boolean, what will we say that is the type of this I comma j? There does not exist an already existing data structure to represent this I comma j. So we have to define a new data structure. Let's say we call that a pair. So we will define a new class pair which will have these two members int I and int j. This is a very common technique that we often have to use in many problems. We have to define custom data structures to represent input or output or anything that is even intermediate. So once we have this class, new class pair, how do we represent our output? That way is that we can represent it in the form of map of pair comma boolean. So pair is the representation of our key. That way we can say that for I comma j pair, we can say whether this was a palindrome or not. Another way of representing the output will be a matrix. A matrix of what size? Matrix of size n cross n, where n is the length of the string. Why? Because consider any element of this matrix. Let's say this one. We can mark it by that this is a I comma j coordinate of this matrix. Now for this I comma j, we can mark the value as true or false. Therefore, similarly, for all possible combinations of I comma j which represent a substring, we can fill the matrix by true or false. Therefore, if we return this matrix, anybody who wants to see which of these substrings are palindromes, which of these are not, can go through this matrix and see that which of these substrings are palindromes. Matrix is also a very common data structure to represent the information where we have to say, hey, that for a pair of I comma j, this is the value. In both matrix and in map, we will be able to retrieve the value for I comma j in just big O of one time, constant time. In fact, if we think about it, matrix is just a form of a map. So we can use either of these two to represent our output for the question. Let's say we go ahead with matrix. Now we know our input and output types. Now before solving this problem, let us try to visualize it. For this problem, we have to check all the substrings of a string, whether these are palindromes or not. Now for that, we need to know how do we check for a particular substring whether this is a palindrome or not. So let's say I get this as a problem that whether the substring between I to j is a palindrome or not. I have to figure this out. Now, one way is obviously that we compare the characters at the two extremes and keep comparing them as we move the pointers ahead. But I want to see if I can make use of the solutions of the previous smaller problems. So let's say if somebody magically gives me answer to this part of the substring, they can tell me whether this part is a palindrome or not. Then can I easily figure out whether this whole is a palindrome or not? Yes, I can. Let us say that he tells me that no, this is not a palindrome. So if this is not a palindrome, I can surely say that overall between I comma j is also not a palindrome. If this is a palindrome, let's say if he says that this is a palindrome, then I just need to check if these two characters are same as well, ai and aj. If these are same, then yes, the whole string is the palindrome, whole substring is the palindrome. If they are not equal, then no, this is not a palindrome. So what are we essentially saying here? We are saying that if for a string s, you want to find out that whether the substring between I and j is a palindrome or not, then you have to check that for that string s, if the string between I plus 1 and j minus 1 is a palindrome. If this is a palindrome and the two extreme characters match, then we can say that this is a palindrome. So what have we done here? We have essentially broken down our bigger problem into smaller problem. And if somebody can tell us the result of the smaller problem, we can deduce the result of the bigger problem. This is recursion. and this is the recursive relation. So in recursion, we break our problem into smaller problem. Why do we say that this is a smaller problem? Because its input size is usually getting smaller. How is the input size is getting smaller? Because here the length was higher than the length of the substring that we are calculating here. So whenever there is a recursion question or recursion part in the question, we should always go through some steps. First of all, we should identify the recursive relation like we did here. Then we should identify input. What will be the input to the recursive function or recursive call? So what will be the input here? We can clearly see that input will be the original string, one starting position and one end position. Because the same method call will be calculating this and the same method call will be calculating this. Now once we identify the input, we will have to also define a base or terminating condition. Why? Because to calculate this, we want this. Then to calculate this, we'll further want another smaller sub problem, and so on it goes on. But it has to terminate somewhere, right? So where would it terminate? This termination usually happens at the smallest of the input sizes. Now, what is the thing that is getting reduced with every smaller subproblem? The length of the substring. So if we consider that the length of the substring is the smallest, let's say 1, then we will get the strings like A, B. So we know that all one size strings are palindromes. So we'll have to write this base or terminating condition that all one size strings are palindromes. Similarly, even for size 2 strings, we can say that AA and BB are palindromes while AB is not. So for size 2, we'll just check that if both the characters are same, then that is a palindrome. So once we are able to define the size 1 and size 2 results, we can terminate the recursion when a larger substring calls happen and they break down into smaller ones and finally eventually they reach size 1 or size 2. Once we can define this base or terminating condition, we may have to often optimize on recursion, because in recursion it is possible that duplicate calculations happen. So if duplicate calculations happen and we want to avoid that, we should store the results somewhere and we should be able to retrieve the result from there if we are encountering the same input again. Let us try to write the algorithm for this problem, checking all substrings for whether they are palindrome or not. To summarize, we have the input as string S and we will represent the output in the form of map. For now, we will do it with matrix later. We have defined a new class pair and we are following these recursion steps. As the first step, we have identified the recursive relation as this, that for checking for I, j, we will check for I plus 1 and j minus 1 and also check whether the extreme characters are equal. So, writing the algorithm for our main function, which takes only string as input, we have to first identify a candidate substring. How do we do that? We loop and we fix an I. Then for that fixed I, we loop again and we fix a j. Then we call some function which will be our recursive function, whether this is a palindrome. And what is the input for the recursive function? As in our second step, the input will be S, I and j. So in this function, what will we do? We will first of all check if the extremes are equal. If these are not equal, we have to anyway return false. But if they are equal and we did not return false, then we will just check is pal S I plus 1 and j minus 1. But is this solution complete? Will this work? Is this recursive solution complete? No, because this will go on infinitely. We will keep going to the next subproblem and so on. So we have to write a base or terminating condition. What will be our base condition? It will depend on our smallest possible size for input. What is smallest possible sizes for our input? It will be when substring is of length 1. How do we represent a substring of length 1 in terms of this input that we are getting? It will be the case when j is equal to I. That is, basically I and j are both pointing to the same character. That will be a substring of length 1. So we have already seen that a substring of length 1 will always be a palindrome, so we can always return true. What will be another base condition? When substring is of just length 2, that is j minus I is equal to 1. Now in that case, if both characters are equal, that means substring is of like AA, BB or so on, then we can return true. Otherwise we have to return false. Now one may think that why did we calculate two base conditions here? We needed to calculate two base conditions because in our recursive relation, our problem is getting reduced into sub-problem by the size of 2. Basically, the input size is getting reduced by size of 2. So we need to be ready with two size base conditions. Now this is a perfectly working recursive method call. This will work. We can calculate whether a particular substring is a palindrome or not through this. But it is a bit inefficient. Why do we say that? Because let's consider this substring. This substring is part of many other substrings. It can be part of this, it can be part of this, and so on. So for all of these substrings, this substring will again and again be calculated here in the recursive calls, which is not efficient. So what we should do? We should somehow store these results. Whenever we have calculated for a particular I, j, let us store it somewhere, and when we are getting the call for a particular I, j, let us just check if we have calculated that earlier. And we can easily do that with the help of map. So now since we have to use map here, that means we have to use one more input other than S, I and J. So a map will also go here. So what have we done here? We have passed a map as input to this function, and after the terminating condition checks, we first check in map if we have already calculated for I, j. If we have, then we directly return and we don't go through further calculations. But how do we put these values in map? Basically, whenever we calculate, before returning, we first put that in map so that we can use it later whenever we encounter it again. At the end, we will have all these results in the map and we can return it or print it, whatever is needed. If we had not used the map and had only used the recursion, our time complexity would be very high. But using the map reduces our time complexity to big O of n square. Why does it do so? Because we are checking for every substring, whether it is a palindrome or not, only once. And in rest of the other cases, whenever we encounter it again, we directly return it in constant time using map. Therefore, our time complexity is big O of n square. And space complexity is also big O of n square because we are storing the results of all substrings in a map. This process of storing the results of a recursive call in a map and then using them later whenever we encounter the same input is called dynamic programming or memoization, or some also call it the top-down dynamic programming. But even this is not optimal. Why? Because here the space is not just occupied by this map but also by the recursion call stack. We know that in recursion we are calling the same function again and again, and that will also occupy memory, one call after the other. A recursion call stack would look something like this: same function and different inputs. This will keep occupying the memory. So if we can avoid recursion altogether while we use the key idea, that will be better. And here comes the bottom-up dynamic programming. Let us now see how will we solve the same problem using bottom-up dynamic programming algorithm. This time we will not use recursion, but we will still use the insight of the recursive relation. In recursion, we were solving the problem top-down, What do we mean by top down? We called for the I comma j, and then while solving for that we saw, okay, we needed to solve this smaller problem, and so we called for this, and so on. In bottom up, we first solve the smaller problems and then we build on to solve the larger problem. So here we first of all declare the matrix. The I comma jth element of this matrix will store whether this substring is a palindrome or not. So we first declare the matrix and we initialize all of it with false. Then we go on to solve the smallest problem. What is the smallest problem? The length 1. For length 1, as we have seen, all of them are palindromes. So we represent that by looping and filling all mat I with true. The second smallest problem is length 2 problem. Now to fill length 2, we again loop. For every I, we know that j will be just the next character. And for length 2, we know how to check whether these are palindromes or not. If both the characters are equal, it will be a palindrome. If both the characters are not equal, it won't be a palindrome. So depending on this condition, we fill mat ij, where j is nothing but I plus 1. Now, how will we fill the matrix for other lengths? We will loop, and in every iteration, we will fix a length. Length of 3, 4, and so on. And in every iteration, we will fill the values for all substrings whose length is this. How will we find all the substrings with a particular length? We will again loop, and in every iteration we will fix a starting position, starting from 0. Once we have fixed the starting position and we know the length, therefore we know the end position. And now we need to fill matrix of I comma j. Now to fill this, we know, do we have all the things that we need? We have ai, we have aj, and we now need matrix of smaller lengths. So we have already filled length 1 and 2. So if length is 3, we have length 1. And once if length is 4, by then we have length 2. If length is 5, by then we will have already filled length 3, and so on. So we can calculate matrix of I comma j and fill it. This is a very common way of iterating over a string to go through all over its substrings. We are going through all the substrings lengthwise. We are first fixing a length and going through all the substrings of that length. Then we increment length by 1, and then we go through all the substrings of that length, and so on. So at the end of this whole algorithm, we will have the results of all substrings in this matrix. How much time will it take? It will take big O of n square. And how much space is it taking? It is still taking big O of n square, but now we are not taking the space taken by recursion call stack. Let us now see how does this all apply to our original problem. So our original problem, we were given a string and we had to return the longest possible palindrome in that string. Now that we know an efficient way of computing all substrings for a string to be palindrome or not, using the bottom-up approach that we saw in previous slide, we can just keep track of the longest palindrome that we have seen so far. And once we are done computing all of this, we can return the longest one. So let's see how will the algorithm look like. We'll simply declare that matrix, we'll fill that all with false. We'll then fill the matrix for the base conditions of length and equal to 1 and length equal to 2, as we saw in previous slide. We'll have two variables to keep track of. These will track the starting position and end position for the longest palindromic substring seen so far. We would have updated these even when we were filling the base conditions. And now when we fill from length 3 till the length of the string, we will update these when we calculate matrix of I comma j. If we calculate matrix of I comma j to be true, we will check that if this palindrome, the new palindrome, is longer than what we have seen so far. If it is longer, then we will update these two coordinates. Therefore, when we are done, these two will have the starting and end position for the longest possible palindromic substring. Now how much will be the time complexity and space complexity? Time complexity will be big O of n square and space complexity will also be big O of n square. But is this efficient? Can we optimize even further? Consider this, that we have a very huge string. Let's say it has some 1000 characters. Then we will have a 1000 cross 1000 matrix that will occupy the space big O of n square. But do we really need all of this information at one single point in any step in the algorithm? No, right? Because whenever we are calculating for a substring of a particular length L, we only need the information for substrings of length L minus 2. If we are at say length 600, then we only need the information of length 598 to calculate the values of length 600. Similarly, if we are calculating for length 601, then we only need the information or the values of all the substrings whose length is 599. Therefore, we don't need the whole 1000 cross 1000 matrix. We only need the information of previous two lengths. Why previous two and why not only previous one? Because consider we are at length 600. We have the information of 598 stored in some array and we could use that to calculate the values for 600. Great. Now we don't need 598, so we fill that array with the values for 600. But now we come to calculate 601 and now we need values for 599. But we don't have 599 stored in that array. We have 600 stored in that array. Therefore, at a time, we will need two lengths, basically two lengths information to be able to compute information for next lengths. Now that the length is fixed, how will we represent the values for a particular length? We can represent that in the form of an array. For example, here let's say length is 598. Then each element of this array or each position can reflect the starting position of that substring. For example, this point here, this will represent length, a substring of length 598 that starts from I is equal to 1. And we can say that this is a palindrome because there is a true stored here. Similarly, substring of length 598 that starts from position 2, this is not a palindrome. And since we need two arrays, we can use one of them as odd length array and we can call another one as the even length array. Now let's see what will be the changes in our algorithm. Here, now we won't be filling any matrix because there is no matrix. We have eliminated that and now we are only dealing with two arrays. One is odd length array and another is even length array. So for all the iterations of this loop, we will fill all the values in a new array. And what will this new array represent? New ARR I. This will represent a substring that starts from position I and is of length this. So we will be filling this value. And how will we fill this value? We will use either the odd length array or the even length array. If the current length is even, let's say 600, then we will use the even length array. And if the current length is odd, let's say 601, then we will use the odd length array. Let us see how will we fill the new ARR I. What does that mean? We want to figure out if the substring that starts from position I and is of length 600 is a palindrome or not. Now for that, apart from the extreme characters, we also need to know that the substring that starts just from the next character, which is I plus 1, but is of length 598 is a palindrome or not, right? Because as per this recursive relation. And we already have this information stored where? In this array, even length array. So we will use the information of 598 length array to compute the value for the 600 length array and we'll fill that in this new ARR I. Our 598 length array would look something like this, where for every position, for every starting position of length this, we would have stored that whether this will be a palindrome or not. Now once we have information on this, we don't need any information on all of the previous length from 1 to 597. Therefore, we can deal with only two arrays. So once we have computed new ARRI, in all the iterations of this loop, we will have a new array ready that will be for L is equal to 600, and we will have this information filled for this length. Now we won't need the 598 information. So at the end of this loop, we will copy this new ARR into the even array. Not in the odd one, because the odd one currently contains the information about 599 length substrings, and we will need them when we will be computing for 601 length substrings. Therefore, in every iteration for a particular length, one of these arrays will get refreshed, and at any point in the algorithm, these two arrays will have the values for the latest lengths that we have calculated. This brings down our space complexity to big O of n from big O of n square. So this is a further optimization that we can do. So far, we have seen recursive and dynamic programming approaches to solving this problem. Let us see another approach to solve this problem. Before going to this approach, let us visualize some more about this problem and make some observations. We are dealing with palindromes here. Now, here are some palindromes that I have written. For every palindrome, we can see that there can be a concept of center. For example, for this center is B, for this too center is B, for this center is BB, because we cannot make one of the element as the center. So if the palindrome is of even length, we can see that the center will be of length 2. Now what do we mean by center here? By center, we mean that if we move towards the left or if we move towards the right, characters will match. Example, here 1 to the left and 1 to the right, both are A. 2 to the left and 2 to the right, both are C. So these are some of the observations that we made, that every palindrome has a center where the characters to the left and characters to the right are equal, and if the palindrome is of even length, then the center length will be 2. With these observations in mind, what could be our approach? We could pick all possible centers, and for every center, we could expand towards left and right and make note of what is the longest possible palindrome formed with this center. And we can return then the longest palindrome found among all of these. How do we pick a center one by one? We can simply iterate over the string from left to right. Then at every position, there are two possible centers. One is the center of length 1 and one is the center of length 2. So let's say if we are at this position, then one possible center is just this A, and another possible center is this AA. How do we expand towards left and right and note the longest possible palindrome? We will have two pointers I and j, which we will initialize from just left and just right to the center. Then we will run a while loop, and till when will we run this while loop? Till the time ai is equal to aj, that the two characters are equal and I should be greater than equal to 0 and j should be less than equal to n minus 1. These two conditions ensure that we do not breach the extremes of the string. Then once we come out of the while loop, we will have the longest possible palindrome with this center. If this palindrome is longer than the one that we have so far, we will update this and it will be used then for the next possible or next candidate palindrome. How much time complexity does this solution take? It takes big O of n square. And how much space complexity does it take? It takes big O of 1. Time complexity is n square because there are two loops, while we do not use any space here, so space is constant. Let us now see a working code for the same algorithm that we just discussed. We get the string s. First of all, we take care of the very base cases, that if this string is empty or the string's length is 1, then the longest palindrome is the string itself. Then we initialize some variables. Most importantly, we initialize the variables that track the longest so far. So we have three variables here: the longest so far's start index, its end index, and the length. Then we initialize some more variables that we will be using. Then we start iterating. In every iteration, we take care of possibilities of two types of centers, center length 1 and center length 2. So in every iteration, we are at a position in a string. We are at a particular position in a string. So first of all, with center length 1, we have two pointers, one to the left of that center and one to the right of that center. Now so far, till the time we have not compared the two pointers, current palindrome longest possible with this center is of length 1, whose start and end index are the same. Then we start expanding towards left and right. We do that using while loop. Till when we run this while loop, till when the characters at the two pointers are equal and the two pointers do not breach the limits of the string. Within this while loop, we keep on updating our variables that track the current palindrome, start index, end index, and its length, and we move the pointers accordingly. Once we come out of the while loop, we have the current palindrome with this as the center, which is the longest possible. So we check that if the current length is greater than the max length we have seen so far. If it is, then we update the three variables. Next, we do for center length 2. But before doing it for center length 2, we need to check if even the center length 2 is possible. For that, the two characters at the center should be equal. So if they are equal, then we again initialize the current palindrome variables, where current length is 2, start index is I, and end index is I plus 1. Again, the two pointers are assigned. We run the while loop to keep track of the current palindrome with these two centers, and we again update the max length. At the end of these iterations, when we have considered all possible centers, we will have the start index and end index of the maximum possible palindrome in this variables. Therefore, we can just simply call the substring method and we can return the relevant substring. Note that the substring method has the second argument as non-inclusive. So we have added a +1 here. You can also find the link to this code in the description. Let us now summarize what all we did, because frankly we did a lot. So first of all, we understood the problem with the help of an example. Then we thought of the simplest possible approach to solve this problem. We thought that let us get all possible substrings in big O of n square using two nested loops. Then we check for every substring that whether this is a palindrome or not. And while checking this, we maintain the longest so far and then we return it. Now we had the problem how to check palindrome, how to check whether a given string is a palindrome or not. So for that we saw a simple approach. We could have two pointers, we could place them to the two extremes, and then we could advance the two pointers towards each other. If the characters at the two pointers keep matching till the two pointers match, that means that a string is a palindrome. That took big O of n time, and that led to our original problem's time complexity to big O of n cube. So when we were searching for inefficiency in this problem, in this solution, we realized one thing, that when we don't have to find whether one particular string is a palindrome or not, we have to find all substrings. We have to check for all substrings of this string, whether they are palindrome or not. And when we are checking for a particular substring, we can make use of a previous substring or a smaller substring calculation. We realized that if we are looking for a substring between I and j and we are checking whether this is a palindrome, we just need to see if the substring between I plus 1 and j minus 1 is a palindrome and the two extreme characters are equal. Thus, we could establish that there is a recursive relation between the two problems. The problem is getting smaller by the size of the substring. So we realized that we could solve using recursion. For recursion, we established this recursive relation. We identified what will be the input for this recursive method. Those input will be s, I and j. Then we identified what will be the base condition or terminating condition for this recursion. we identified that the terminating conditions would be when length reaches 1 or length reaches 2. We then used memoization to better the time complexity of our recursive solution. In this memoization, whenever we were able to calculate any result using recursion, we put that into a map. And before actually calculating any result for any input, we checked if we have already calculated that and stored in the map. If we had it in the map, we would return the result directly from the map. Then we realized that even with memoization, we are occupying a lot of space because of recursion call stack. So it would be great if we could not, or we could basically completely skip the use of recursive calls. So we came up with another approach. That approach was bottom-up approach, and we used matrix for this. And in the bottom-up approach, we filled the values for all I, j in a matrix. And in the matrix's I, j element basically denoted whether the substring from I to j is a palindrome or not. This is a very common approach that will be used in multiple problems, where we first identify a recursive relation, we identify the inputs, we identify the base conditions, then we do a top to bottom dynamic programming or memoization using map, and then we go towards bottom up. Once we had this way of checking palindrome for all substrings of a string, we applied this to our original problem. Here, all we had to do while checking all substrings for being palindromes or not was keep track of the longest palindrome found so far, and then later we can return that. Then we further realized that we don't actually need the whole matrix. We only needed the last two lengths computation to get the current lengths computation. So instead of the matrix, we could do with only two arrays, and hence we could reduce the time complexity to space complexity to big O of n. Then we saw another approach. This was a non-recursive approach. Here we further made an observation about palindromes that all palindromes would have a center, and if the palindrome is of even length, that will have a center of length 2. So we considered every center one by one, and we expanded from that center towards left and right. We kept a note of the longest possible palindrome using that center, and then we kept track of the longest we have seen so far and kept updating it. And then finally we returned the answer. We wrote the algorithm for it, and we also saw a code walkthrough for this algorithm. This is it for this video. We will meet again in the next video with some other problem. Thanks for watching.